Hey everyone, now that you're done learning how to find the pH of strong acid and strong base, time for us to get one level closer to taming the beast by learning how to find the pH of a weak acid or a weak base. And here's the problem. How can you find a weak acid and weak base if they don't dissociate fully, right? And here we have two dissociation constants for you to find the pH of a weak acid or a weak base. And the first constant is called the acid dissociation constant. If you recall, or you should know that a weak acid exists in a equilibrium, and we can then have the Kc equation. Once more, we know that the H2O concentration H2O is going to remain relatively constant at 55.6 because the dissociation is going to be negligible as compared to the value 55.6. That's why we treat it as a constant, and we can combine two constants together, namely Kc and H2O, to Ka. And this is the acid equation for the acid dissociation constant Ka, units important mole per dm3. Alright? Now, essentially how to remember this equation is basically the Kc equation without the H2O, and instead of C, it is A. Likewise, this is for weak acid. We have the one for the weak base as well, called the base dissociation constant, and you can probably guess it, Kb. Logic is the same, and instead of H plus, H3O plus, instead of A minus, it is Hb plus OH minus with the concentration of base as the denominator. Nothing changes that much either. Units is still mole per dm3. Alright, so we have these two formulas right here. And the theory is that if you see the values of Ka and Kb given, you should automatically think that you're dealing with either a weak acid or a weak base. Alright, because strong acids and strong base do not exactly have a Ka or Kb value. You can probably imagine why. Because the concentration remaining is super duper low, the value is really close to infinity. I mean, approaches infinity, no such thing as close to infinity, rather approaches infinity. Alright, it's super duper big. Okay, so theory behind finding pH and pOH of weak acids and bases. Once again, they partially dissociate in water, so you cannot just plug in the values from the concentration. And instead use the Ka and Kb equations as we've seen right here. Now, Ka and Kb will be provided. The values will be provided. And you need to know how to create the equation to find pH and pOH. And if you notice, alright, we are given this. You still need this, alright, because we know that if you recall from the equilibrium in weak acids or equilibrium in weak bases, it's H3O plus and concentration of A minus would be the same, and basically it's just X squared, alright, and you still need the concentration of the weak acid or weak base. And the thing is, we're going to assume it to remain constant throughout, because the dissociation, aka the concentration H plus or concentration OH minus X, is going to be negligible relative to the concentration of the weak acid or weak base used. Now, what do I mean? We have this first example right here. Benzoic acid, Ka value is given, concentration of weak benzoic acid is given. Because we know that it exists in an equilibrium, we can then do the ice table as we usually do for our equilibria questions. Now, if we assume that benzoic acid dissociates and X mole dm cube of benzoic acid is dissociated, we then have X mole dm cube of benzoic ion formed, X mole dm cube of H3O plus formed. This then leads us to 0.35 minus X for our benzoic acid, X mole dm cube for both our hydronium ion and the benzoate ion. Now, because this value of X is very low, relative to 0.35, we're gonna assume that this equilibrium amount of benzoic acid is relatively constant at 0.35. Now, do not put this 0.35 inside the ice table. Ultimately, it is still 0.35 minus X. It's just that when our calculation for finding pH and pOH of weak acid and weak bases, we're gonna assume it to be 0.35. Of course, there are exceptions, and you see that exception later on. Alright, so back to theory. You might wonder, do we need to consider concentration of H plus and OH minus from the ionization of water? Answer is no. Why? Two scenarios. If the theoretical H plus or OH minus from the acid and base is lower, then the weak acid or weak base will not dissociate at all. Alright, because if you remember the idea of QC, QC is greater than KC, and QC is already greater than KC before any acid or base is going to dissociate, then the weak acid and weak base will not even dissociate at all. Hence, they will not even dissociate. Alright? Now, otherwise, we just assume that the H plus or OH minus from the ionization of water is negligible. And we're just going to ignore that completely. Alright? So, basically, very simple. Weak acids, weak bases, you want to find pH or POH. Don't need to consider H plus or OH minus from the auto-ionization of water. And let us begin with the first example of benzoic acid, going back to it again. Alright? So we're going to use the Ka equation. So it's good to start off with the Ka equation. Alright? Where we have, well, the benzoate ion, the hydronium ion, or the hydrogen ion, which one you prefer, and then the concentration of the benzoic acid. Okay, HKa is given 5.71 times 10 power minus 5. We established that there is going to be x square of on top, right? So all we can do is simply concentration of hydrogen ion square below 0.35 minus x, but because we say that x is so low, then the HA or the concentration of H plus is super low compared to HA, we're gonna assume that the concentration of benzoic acid remains the same. Gonna skip some steps ahead. So it's just basically just very simple mathematical manipulation and simplification. Now we want to find pH, right? So we're not looking at the concentration of H plus, but finding pH. So it is simply applying the minus log. Now, what do you notice is that, hey, why can't I just write this equation directly, right? Just find pH directly. Answer is you can actually, but there's a caveat to it. If and only if all the H plus or hydronium ions come from HA alone. So if there are two weak acids, then you cannot use this equation. In fact, it's actually a bit more complicated. If there's only one acid, then yes, you can use this equation, all right? Because don't forget, pH measures the total concentration of H plus available. If the total concentration of H plus is not only coming from HA, then of course this doesn't hold. All right, and of course the idea of equilibrium will then come in, and it's a lot more complicated and it's not required in the H2 chemistry syllabus. All right, but nonetheless, if it is, you can directly plug in either of these formulas. Personally, I do this because it's easy, so I have to type in the square root sign. Otherwise, all right, the answer is simply 2.3496, 3SF 2.35. Now, do you need to write these few steps ahead? Answer is no. All right, you can actually just ignore it and just immediately write this down if you can remember, or if you can derive it very quickly in your head. Once again, you don't need to memorize this equation right here, because as you can see from here, it is derivable. All right, otherwise, let's move on to example number 2, ammonia. Kb of ammonia is given 1.8 times 10 power minus 5 mole dm cube. Calculate the pH of a 0.70 mole per dm cube solution of ammonia at 25 degrees Celsius. All right, now Kb, all right, you can write this down, which is basically the ammonium ion, the conjugate acid, the hydroxide ion divided by the ammonia. Once again, this remains relatively constant at 0.7. These two have the same concentrations. So what we're going to do is 1.80 times 10 power minus 5. In fact, I'm going to skip some steps. All right, then we have OH minus equals to square root of this, right? You see, it's the same idea. But now, remember, this is OH minus. You then get POH and not pH. All right, minus log 1.80 times 10 power minus 5 times 0.70. All right, you want to find pH? Sure, go ahead. Again, using the idea of pH plus POH equals to 14 at 25 degrees Celsius. 14 plus this, so it's simply 14 minus whatever value that we get right there. All right, so this value right here we get is 2.4498, so 2.45. So minus 2.45 equals to 11.55, 11.6. Okay. So again, all right, you can also use the formula from just now, right? This is already the same. You just plug this in directly. Again, don't need to memorize. It is derivable right here. In fact, you can even put as a case for pH, right? pH equals to 14 plus root, or rather plus 0.5 log Kb and then the concentration of the base as well. All right, so that will work. So we could have just done 14 plus log 1.8 times 10 power minus 5 times 0.70 and then half of that. Okay, so that is basically example number 2, but take note it is POH and the question wants pH. All right, so do not make that careless mistake of initially putting that as pH. All right, if you did, you should ring some bells, right? How can ammonia have a pH of 2.45, right? Doesn't make sense. Okay, so that's how you can check your work as well. Now, third example. Now it's different. Instead of finding pH, we are given the pH, now requiring us to find Ka. Here's the catch. All right, if you remember from our ice table earlier, where we have, all right, let's take this example. Ha is 0.1. So initially, Ha is 0.1 minus X. Then we have 0.1 minus X. Then H plus is 0. Then we have plus X. Now it's X, right? Here's the thing. Now we are given the concentration of the H plus. How? We are given pH to be 3. So if pH is 3, we know that X is now has a value of 10 power minus 3. And because we now know the value of X, we can no longer make that assumption. Since H plus is known, we cannot assume that the concentration of H plus is negligible relative to HA anymore. Because we now know the value, we can use it. As such, this is where the ice table still remains relevant and you still need to be careful of this. So long story short, you must be aware that you are making this assumption whenever you're finding pH and POH of a weak acid and weak bases, and when you know the H plus, you cannot make that assumption anymore. Alright, so otherwise, let's start calculating the Ka. Okay, so Ka again, conjugate base, hydrogen ion or hydronium ion over the concentration of Ha, which H plus, we know that is 10 power minus 3, A minus, well, same concentration as H plus, so we can just square it. Ha started with 0.1. How much does it dissociate? 10 power minus 3. Alright, so no longer just 0.1. We don't make that assumption anymore because we know that X is 10 power minus 3. So what does this give us? This gives us 1.010101 times 10 power minus 5, 1.01 times 10 power minus 5. Don't forget your units, mole per dm cube. Alright, don't forget this. If you leave this out, GG. You lose half mark, you might even lose 1 mark. pKa, basically applying the minus log to it. So minus log 1.01 times 10 power minus 5. You then have 4.9956, round it up to 3SF, 5.00. Okay, so once again, I will reiterate, if you know H+, then we can assume that it's negligible. Alright, so formulas, we have the two constants right here, and then followed by the finding of pH or POH of a weak acid or weak base. Of course, the condition is that all the H+ only comes from the weak acid. Likewise, all the OH- come only from the weak base. Of course, then, if you want to find the pH of a weak base, you just need to then put in 14 minus away POH, Of course, this is available at 25 degrees Celsius because this is the value of Kw at 25 degrees Celsius. Alternatively, 14 plus 0.5 log Kv times the concentration of B. Alright, so that is the end of the second level, and I'll leave you guys right here as Sean will be taking over me, bring you through the last 3 levels as you fight valiantly to tame the beast and make a new friend. And here I am signing off as a small lizard, bidding you goodbye and all the best for your journey ahead.